Hello, this is me, Samir Bauza. So I'm going to speak about the effect on hardness and microstructure of the workpiece on the toolware of cubic boron, Nitride, CBN, cutting tools, and hard turning application. So my objective purpose for this topic is to demonstrate the variation in the tool life or the toolware of the CBN tool with hardness and the microstructure of the workpiece with the flangware plot. So this is a summary bullet point from the paper I wrote for this topic. So I'm going to go over this briefly. So the tool life or the toolware. I'm going to say toolware. The toolware of the CPN decrease with the increase in the cutting speed until to the maximum point, and the decrease of the toolware due to the buildup of protective layer, and after that maximum point is increasing. Now similarly, there is a similar downward trend of the toolware, which is that it goes down with increasing hardness for the workpiece hardness of below 50 Rockwell hardness, and this is due to the reduction in cutting force. And after that, the toolware increases for hardness above 50. Now, besides the hardness and the cutting speed, the most important parameter that affect the toolware is the different amount of carbide in the workpiece. Now, all of these points I'm going to elaborate more with the figures next slide. So the two figures, so the PCB and cotton tool is usually described in terms of slang and wear, and the tool life is predominantly defined by wear due to the significant influence of the parameter on the surface finish and the dimensional accuracy of the machine part. Now, so this wear plot, it shows the wear curve with the harness for the CP and cotton tool beside the ceramic tool and P10 tool on the workpiece, which is ASI 4340, and the cutting speed 100 meter per minute, a feed rate of 0.1 millimeter per revolution, a depth of cut 0.2 millimeter. So as you can see from the line for the GBN, when you turn hardening tail below 50, the cotton temperature will increase with the hardening. So when the cotton temperature increases, the workpiece gets more softer, reduce the cutting force on the workpiece. So they reduce the tool wear. You can see going down. Now the same trend of the tool wear going down happen over there on the left, this plot. So in this plot it shows the variation of tool life with this speed. So the tool life it increases upward until the speed of 80. So in other words, the tool wear is decreased until the speed is 80. So this is due to the buildup of the other layer on the tool face that is formed by the abrasion of the binder of the tool by the hard carbide of the workpiece. So the buildup is at a protective layer by reducing um, the deterioration of the group of picks during cutting. So that's why the tool will go down. The same thing as tool life will go up until the speed is 80, because then after 80 the train goes down because the higher cutting speed cause a more higher cutting temperature, which may soften the adhere layer and cause it to get easily abraded. So the tool wear will go up after the speed of 80, but it's the same thing as tool life going down after the speed. Now again, similarly, when on the plot on the right, when you are turning hardened steel above 50, the tool will increase because at the at the cutting temperature gradually reduces from the high value, it results in the latter softening of the workpiece. So it reduces the cutting force. So when the cutting force is less, the now the cutting force is increased. So furthermore, the cutting force also increased because of the formation of the sawtooth chip on the workpiece. So there is a high shear stress and strain on the sawtooth chip that cause the high increase in cutting force, and all of these contribute to high tool wear. So now again, and so this plot on the left. So these two plots, this one on the left is for the hardness of 50, and this on the right is for the hardness of 57. So as can be seen, the tool life overall is lesser for the hardness of 57, which is for the case of hardness above 50, where the tool life generally goes down according to this. But now, next slide, there have been a lot of experiments on many different types of hardening steel, all of them which is hardened to the same hardness of 54, which shows that the varying two-way rate, which it indicated the influence of the microstructure of the workpiece on the toolware rather than the hardness. So, so these four steel 100 CR6, which is ASI 52100, and the hot work the anxiety to the um, and to do another hot work the so now the slang wave plot so the slang wave rate for the four different material with the time at one cutting speed of 180 meter per minute. Now, based on those, based on this plot, all of the four tiers are grouped into two groups: the high tool and the low tool. Altogether, for 16 tool experiments for each of the four materials being machined at two different cutting speed, which is 180 meter per minute and 230 meter per minute, and 2 feet width of 0.08 and 0.12 millimeter per revolution. So from the microscopic result, this, this steel, this steel and this steel, they both have the high amount of M3C7 carbide. So they have a very high carbide content. So from this plot, you can be seen that the high tool will due to the high carbide content. Now, furthermore, in this plot at the bottom, it will show the different hardness for the different type of carbide. So I can be seeing that M753 has a very high hardness. So it can be suggested that it is due to the high hardness of the MC carbide that is causing the high tool wear rate in the case of the material and the material. Now, this plot also indicates the that the hardness is different for different type of carbide, and since the four different materials have different type of carbide, it can be observed that the two wear which are different for the four different materials due to the different hardness of the carbide content. That okay, I think that's it. Thank you.